Welcome to the second part of Module 2, the chapter is Central Processing Unit, and this time we'll be studying the stack organization that is used in a CPU. Most CPUs have a stack, so the function of a stack is basically last in, first out. Okay, so whatever element enters in the last is the first one to leave the list. It is a storage device, so it basically stores information in such a manner that the item that was last stored is the one that is first received. Okay, so to keep track of stack locations, there is an address register, and it is used to count only after an initial value is stored into it. The address that register is called a stack pointer, and it holds the address for the stack. Because its value always points to the top of the item, that's what's called a stack pointer. The push pop operations. Stacks have basically two operations, insertion or deletion, and the insertion is called the push operation. This is because it can be thought of as the result of pushing a new item onto the top of the stack. The pop, on the other hand, is the deletion, and this can be thought of the removing of an item from the top of the stack, thus calling it a pop operation. These operations are performed by either incrementing or decrementing the stack pointer register. Thus, when the top is incremented, you can add something, and when it is decremented, that deletes the top of the stack. Register stack. So a stack can be placed in a portion of large memory, or it can be organized as a collection of finite number of register words. So the stack can be used as a storage memory where we have full and empty. These are two 1-bit flip-flops. The stack pointer points towards the top element. We store the elements over here, and this is the address. So we may have, in this case, we have a 64-bit stack, and the data register stores the instruction or the data that is to be added to the stack next, or the data that is deleted is also stored into the DR. This here is a 64-word register stack. The stack pointer register SP contains the binary number whose value is equal to the address of the word where the current top of stack is. So if you place three items in a stack A, B and C, then item C will be on the top because A will be at the bottom, and thus the content of stack pointer is now 3 because it's the third element. To remove the top item, the stack is popped by reading the memory word at least at the address 3 and then decrementing the content of SP. So whatever memory word we have at address 3 is stored into the DR, which is the data register, and then the stack pointer is decremented. Item B will be on top of stack, and stack pointer will hold the address 2 once we pop the item C. To insert a new item, the stack is pushed by incrementing SP, so SP plus 1, and then we write the word in the next higher location of the stack. Note that the item C has been read out but not physically removed. So whenever we decrement the stack pointer, it's basically that we are not pointing towards the topmost element anymore. Pop basically does not delete the element, it just stops pointing towards C. So it doesn't matter whether it's removed or not. Whenever we push a new item, then C is overwritten by the new item. It is never truly deleted from the stack. In a 64-word stack, the stack pointer comprises of 6 bits. So 6 bits can show you different combinations all the way up to 64. It therefore cannot exceed a number greater than 63. So from 0 to 63 is the range, and anything above 63 will cause overflow in the stack, which may cause interrupt issues. When 63 is incremented by 1, the result is 0, since the 63 binary plus 1 leads to all zeros, and stack pointer cannot accommodate anything more than 6 least significant bits. Similarly, when the stack pointer is completely 0 and it is decremented, then the result causes 7 ones, which is also not possible since the stack is empty and it can only hold 6 bits. The 1-bit register full is set to 1 when the stack is full, and the empty is set to 1 when the stack is empty. So the data register holds the binary data to be written or read out of the stack. The stack pointer is cleared to 0 initially, and then when it is cleared to 0, this means the stack is empty. Hence empty is set to 1 and full is set to 0. Full is set to 0 because the stack is empty, and stack will now point towards the address 0, and the stack is empty and not full. If the stack is not full, if full equals to 0, then a new item is inserted with the push operation. The new item is deleted from the stack if the stack is not empty. So the pop operation consists of the following sequence. If we are to push, then initially stack pointer is 0, empty is 1, that means the stack is empty, and full is 0, that means we do not have anything in the stack. So in order to push, we are going to increment the stack pointer by 1, and then from the data register we are going to store the item into the memory address of the stack pointer, and then we are going to check the status. So if stack is full, then full is 1 and empty becomes 0. For the pop operation, on the other hand, the stack pointer has in this case we've shown 0 and the stack is empty and full is 0. So in order to pop an item, we are supposed to go to the memory address of the top of the stack, and we are supposed to save it to the data register, and then we are going to decrement stack pointer by -1, and then if it is 0, if the stack pointer is 0, thus the stack is empty and full will be set to 0. In this case, stack pointer does not have to be cannot be 0 and nor can it be empty, because once the stack is empty, the pop operation cannot be performed. Hence the stack pointer has to be pointing to any other index, and it could be 1, and if it's 1, then at the next increment at the next decrement the stack would become empty. Memory stack. So a stack can also be used to implement random access memory attached to a CPU. The implementation of stack in the CPU is done by assigning a portion of the memory. So the stack is given a small portion of the memory. We do not give the entire memory to the stack. And the processor register is used as a stack pointer. The stack pointer SP points to the top of the stack, and we use it to push or pop items in and from the stack. So this is an example of how a memory can be used for implementing stack. The stack address starts from 4000 and it is decremented, and a certain area is given to stack. So we can see we have given from 4000 all the way to 3000 has been given to the stack, and we have the data register that stores the data that will be added to the stack, and we have the CPU register that is used as a stack pointer. Either of the three registers, PC, AR, and SP, can provide an address for the memory. PC is used during the fetch phase, and AR is used during the execute phase, and finally the stack pointer value is 4001, and the stack grows with decreasing addresses. So as we go higher up in the stack, the address is going to decrease, so it is basically decrementing. Thus, the first item stored in the stack is at the address 4000, because 4001 was the initial stack. So whenever we store a new address, we are going to increment by 1 stack pointer, and then we are going to be storing the value at 4000. The second item will be stored at 3999 and so on all the way up to 3000. A portion of the memory is used as a stack with the processor register as a stack pointer. We can push by decrementing the stack pointer, since in this case 4000 was the start and we are going backwards towards 3000. Thus we will decrement, and then from the data register we are going to transfer it to the memory address of the stack pointer. The pop operation, on the other hand, we are going to take the data from the memory address of the stack pointer and we are going to store it with the DR, and finally the stack pointer will be incremented, which means 3999 will go to 400. That means the size of the stack has been reduced. So if we have a question where we have stack pointer starting at this is the stack pointer address, and in the case of a 64-word register, how many items are there in the stack if full equals to 1 and empty is 0? This means the stack is full. We are referring to the number of items in this case, which will be 64. Do not mistake this for being the index. The maximum index of a stack is going to be 63, because we will be starting from the 0th index all the way to 63, but the total number of items that are stored in a stack are going to be 64. On the second case, when full is 0 and empty is 1, this means that the stack is empty, hence there is no items in the stack. Another question says that a stack is organized such that the stack pointer always points to the next empty location on the stack. This means that the stack pointer can be initialized to 4000, and as it was shown in the figure, for the memory stack, and the first item in the stack is stored at the position at the location 4000. List the micro operations for the push and pop operations. So over here we are going to be showing the what the micro operations are going to be if we need to push a value or if we need to pop a value. Just as we had seen, whenever we are pushing a value in a stack organization that is used in a memory, we start from 4000 and then we are going backwards in the memory address towards 3000. Hence the stack pointer is decremented in this case, and the memory and the data register that has the value is then stored into the memory address of the stack pointer. This is the push case. For the pop case, on the other hand, we take the memory from the stack pointer. So if it is 3998, we'll take the memory and store it into the data register, and then finally we're going to increment the stack pointer, so it will go from 3998 towards 3999. Hence the third index will be removed. Thank you, and see you in the next video.